There's a lake hidden at the bottom of the ocean. It has a visible surface. It has a shoreline. Waves can move across it and streams can flow away from it. But this lake is not filled with fresh water. It is made from water so intensely salty that it remains separate from the ocean surrounding it. To a camera descending through the darkness, the boundary can look almost impossible. The seafloor appears below. Then, resting upon it, is another body of water, an ocean beneath the ocean. These formations are called brine pools. Some are only a few feet across. Others can stretch for miles. They have been discovered in several deep-sea regions, including the Gulf of Mexico, the Red Sea, and the Mediterranean. One brine lake investigated in the Gulf was approximately 180 meters wide and 4 meters deep. Its water contained roughly twice as much salt as ordinary seawater. Scientists could see pale material floating inside it. Samples later showed that no visible animals were living on its bottom. But the story of these strange lakes began long before humans ever saw them. More than 100 million years ago, during the Jurassic period, the early Gulf of Mexico was partly cut off from the open ocean. Seawater entered the basin and evaporated. The water disappeared, but the salt remained. Over immense spans of time, new layers of sediment buried those deposits beneath the seafloor. In some places, the ancient salt became kilometers thick. Salt does not always remain still underground. Under pressure, it can deform and rise through the sediment, creating domes, ridges, fractures, and valleys. When seawater moves through these buried deposits, it dissolves the ancient salt. The result is brine, water carrying an extraordinary concentration of dissolved minerals. Eventually, that brine can escape through cracks in the seafloor. Ordinary seawater does not simply mix with it. The salt makes the brine much denser. It sinks, follows the contours of the seabed, and gathers in the lowest places. Drop by drop, an underwater lake begins to form. Because the two bodies of water have different densities, a visible boundary can appear between them. The effect is so convincing that remotely operated vehicles seem to hover above an alien coastline. There can be beaches, there can be ripples, there can even be waterfalls, with dense brine spilling over a ledge and flowing downward through the sea. But this beautiful boundary conceals a hostile world. Inside many brine pools, oxygen is scarce or completely absent. Some contain high concentrations of methane and hydrogen sulfide. For animals adapted to normal seawater, entering such a pool can be dangerous. The sudden change in salinity interferes with the way their bodies regulate water and salt. A lack of oxygen can prevent them from breathing, while hydrogen sulfide can be toxic. This has given some brine pools the reputation of being death traps on the seafloor. But the truth is more complicated. These are not empty places. They are ecosystems built around a form of life that does not depend on sunlight. At the surface of our planet, most food chains begin with photosynthesis. Plants and microscopic algae capture energy from the sun. Other organisms consume them, and that energy moves through the ecosystem. At the bottom of the deep ocean, sunlight never arrives. Around brine pools and cold seeps, certain microorganisms use chemical reactions instead. They can obtain energy from substances such as methane and hydrogen sulfide. This process is called chemosynthesis. The microorganisms may look insignificant, but entire communities can depend on them. Large mussel beds have been found along the edges of brine pools. Some of these mussels contain bacteria inside their bodies. The bacteria turn chemicals from the seep into usable energy, helping to feed their hosts. Tube worms, crabs, shrimp, anemones, sea stars, and fish may also gather near the boundary. From a distance, the lake can resemble an oasis surrounded by life. Yet the richest communities often exist only within a narrow zone, too far from the pool, and there may not be enough chemical energy. Too far inside it, and the extreme conditions become intolerable. Life gathers along the shoreline between those two worlds. Some microbes go even farther. They can survive within the oxygen-free brine itself, tolerating pressures, salinities, and chemical conditions that would kill most familiar organisms. Scientists study these extremophiles partly because they expand our understanding of where life is possible. They may also offer clues about other worlds. Jupiter's moon. Europa is believed to hide a salty ocean beneath its icy crust. Saturn's moon, Enceladus, sends material from its subsurface ocean into space through enormous plumes. If life exists in those dark oceans, it cannot rely on sunlight in the same way that life at Earth's surface does. A brine pool on our own seafloor may therefore serve as a natural laboratory for imagining biology beyond Earth. A place that looks dead may reveal how life survives when almost everything familiar has disappeared. Even reaching these lakes is difficult. Many lie more than a kilometer below the surface. Some are far deeper. At those depths, the pressure can crush ordinary equipment. There is no natural light. Temperatures are low, and research vessels may have only a limited amount of time above each location. Scientists rely on submersibles and remotely operated vehicles equipped with cameras, lights, sampling containers, and robotic arms. Approaching the surface of a brine pool requires care. A vehicle that descends into dense brine can behave differently because its buoyancy changes. The salty water can also be corrosive, and disturbing the boundary may make observations more difficult. Researchers collect water and sediment from multiple positions, above the pool, at its edge, and within its interior. The differences can be dramatic. Only a short distance may separate oxygenated seawater filled with animals from an anoxic basin where no visible animal life survives. Every expedition reveals only a small part of the system. Some brine pools appear relatively stable. Others overflow and create rivers through the seabed. Their chemistry can vary, and each one can support a different community. They also preserve information. In oxygen-poor environments, decomposition may happen differently. Sediments can retain chemical and biological records that help researchers reconstruct changes in the ocean. But these places should not be confused with the much larger seasonal dead zones, produced when nutrient pollution contributes to oxygen loss. Both can lack oxygen, but deep-sea brine pools are natural geological formations created by concentrated saltwater and the movement of ancient salt deposits. Their existence reminds us how incomplete our picture of Earth remains. For most of human history, no one had seen them. People crossed the ocean, built cities beside it, and drew maps of its surface without knowing that lakes, rivers, and waterfalls were hidden below. Even today, much of the deep sea floor has never been observed directly. There may be other brine systems, strange organisms, and chemical environments waiting in places no camera has visited. So imagine descending through more than a kilometer of black water. The last trace of sunlight disappears far above you. Then your lights reach the bottom. A shoreline emerges from the darkness. Ripples move across a surface that should not exist. Animals gather at its edge, but almost none cross the boundary. Beneath an ocean covering much of our planet, another body of water has been waiting in silence. A lake with no sky, a shoreline with no land, and an ecosystem powered not by sunlight, but by chemicals rising from the ancient earth.